Section 3 takes us to probability of multiple events occurring together. So we need to talk about independent events and dependent events. We've kind of already talked about dependent events, but now we've got to talk about them together. We need to always think about whether or not these events that we're talking about are dependent or independent. So first of all, independent event. The outcome of an event does not affect the outcome of another event. We've seen that a couple of times. First, flipping a coin and drawing a card. If I flip a coin with one hand and then I reach into a pile of cards with the other hand, it doesn't matter if I come up with heads or tails. That's not going to affect the outcome of me drawing that card. Or it doesn't matter what card I draw, when I flip that coin, I can either still get heads or tails. So those are independent events. They do not matter compared to one another. Rolling one die, then rolling another. This is the most independent event we've dealt with so far. The first die rolled does not affect the outcome of the second die rolled. There's this phrase right here called with replacement. With replacement causes an event or a couple of events to be independent. For example, if you pick a card out of the deck and then you pick another card out of the deck, would that be an independent situation? No, it would not, because once you pick that first card, the probabilities change for the second card. But if you pick a card out of the deck and then you put that card back, in other words, you replace the card, and then you draw a second card, are those independent events? Yes, they are, because the deck has been restored to its original number of cards. And as soon as that happens, then the probability of your first card is the same as your probability of the second card. If I have 5 poker chips in a bag, and I reach into the bag and I pull out one poker chip and it's blue, there's only one blue chip in the bag. I put that blue chip back in the bag, and then I reach out and pull a second poker chip. Do I have the same probability as I had the first time around? The answer is yes, and that makes it an independent event. Dependent events. The outcome of an event does affect the outcome of another event. So for example, I deal you a king, and then I deal you another card. There's now only 3 kings in the deck. Not only that, but there's only 51 cards left in the deck. So the probabilities have changed as far as what you're likely to get on your next card. So that is a dependent event. Pulling a colored marble out of a bag, and then pulling another colored marble out of the same bag without putting that first one back in. This is going to change your probabilities as well. So that makes it a dependent event. Dependent events are called events that occur without replacement. I don't put it back before I take another. That makes the event dependent. Okay. So now that we know those vocab words, are these events independent or dependent? So for the first one, you roll a die and then you spin a spinner. They're independent. The die and the spinner are completely separate from each other. Independent. How about the second one? You draw a card from a deck and then you draw another. That's dependent unless it says you put the card back. Then it would be independent, but that's not what it says, so therefore it's dependent. The third one, you pull a coin from your pocket, and then you put it back, and then you pull a coin from your pocket again. Those are independent. No. Nope. Doesn't matter. If 2 events are independent, then you have this formula right here. The probability of A and B occurring. These are for independent events only. Is the probability of the first event times the probability of the second event. This is the fundamental counting principle right here. We're just calling them independent events here. So for example, at a picnic there are 10 diet drinks and 5 regular drinks. Like picture like in a cooler with ice, like cans of pop or something. There are also 8 bags of fat-free chips and 12 bags of regular chips. So in like Santa's bag or something where you can't look in, there's all these bags of chips. If you grab a drink and a bag of chips without looking, what is the probability that you get a diet drink and fat-free chips? Whether that makes your day or not, that's what we're looking for. So what's the probability? of getting a diet drink and fat-free chips? Well, first of all, are these independent events or dependent events? They're independent events, and because they're independent, I can use this formula right here, basically the fundamental counting principle. So I'm going to write the probability of what? Diet and fat-free. And we know what those mean. Is the probability of grabbing a diet out of the cooler times the probability of grabbing fat-free out of the bag. So what is the probability of grabbing diet out of the cooler? So there are 10 diet drinks in the bag, in the cooler, out of 15 total drinks. Wins over weighs. Times, now for the chips, it looks like there's 8 bags of fat-free chips. So I can get 8 ways to win there out of how many bags of chips? There's 20 bags of chips in that grab bag. Now we just multiply those things together. That becomes what? Let's leave it as a fraction. 6/15. No. Yeah, it's 4/15. Okay, so there's the fraction, and then as a percent, that would be, what did you say? 26.7%. Got confused with my percent and my decimal. So that's how you do that. The probability of the first thing occurring times the probability of the second thing occurring, it's basically the same as what we're doing with the dice. It's just not, now we're talking about different types of problems. So in the problem above, what is the probability of getting a regular drink and regular chips when you do this random draw? Okay, now keep in mind 26.7%. So about a quarter of the time, if you were looking for a diet drink and diet or fat-free chips, about a quarter of the time you would actually get that. So let's see what the probability is of getting a regular drink and regular chips now. So what's my setup? 5/15. Before that. Okay, turns out the word and is important. And now what do we get? There are 5 regular drinks out of 15 in the cooler, times there are 12 bags of regular chips out of 20 in the bag. What does that give me? 1/5, yeah, when you simplify it down. 1/5, which is 20%. So that's how you do these. It's basically the fundamental counting principle, but each one you have to figure out the probability for each independent event. 9 through 17L, how many problems is that?
8.
9 problems. The next little block of stuff in this section is mutually exclusive events. I've subtly said this phrase a couple of times, now we actually get to know what it means. Mutually exclusive, you may have heard before, used elsewhere. But in math, it means that 2 events can't possibly occur at the same time. It's impossible for them to occur at the same time. So if A and B are mutually exclusive events, then the probability of A and B occurring at the same time is 0, because they can't possibly occur together at the same time. For example, determine whether each event is mutually exclusive. Rolling a single die, and on that one roll that you rolled, you get a 2 and a 3. Can that happen? That is impossible, yeah. Which means that getting a 2 and a 3 at the same time on the same die is a mutually exclusive event. So the answer here is yes, it is a mutually exclusive event. What about rolling a single die and getting an even number and a multiple of 3? Is that possible? Yes? How? Yeah, the number 6 is even and it's a multiple of 3. So is this mutually exclusive? No. Rolling a single die and getting an even number and a prime number. Is that possible? Yes? What number? 2 is the only even prime number. So the answer here is, these are not, determine whether the events are mutually exclusive. This is not mutually exclusive. So why don't you put yes, mutually exclusive, no, no. How about that last one? Rolling a single die and getting an even number and a number less than 2. So, right, no, which means yes. Are these mutually exclusive? Yes, these are mutually exclusive. Why are these mutually exclusive? Right, the only number less than 2 on a die is 1, and 1 is odd. So this is mutually exclusive. All right, so the previous examples involved events A and B occurring together. If you have events A or B, the probabilities change a little bit. Your formula goes from PA and B to PA or B, and it switches from multiplying the two together to just adding them. We have the probability of event A occurring plus the probability of event B occurring. But then I got to subtract off the probability of events A and B occurring together. So this last little question right here, note the last term in the formula, this guy right here. If A and B are mutually exclusive, what happens to that term? It disappears. Because if they're mutually exclusive, then the probability of both of those events occurring at the same time is 0, which means this term would go away. And then you're just left with these two probabilities being added together. So, for example, Bob's High School, a student can take one foreign language per term. About 37% of the students take Spanish. About 15% of the students take French. What is the probability that a student chosen at random is taking Spanish or French? That's right. It says only one foreign language per term. So these are mutually exclusive events. But I am looking for Spanish or French, which means I'm using this formula right here. What happens to this term? Goes away. They're mutually exclusive events. So now I just got to figure out the probability of a student taking event A, which we can call Spanish. What's the probability of a student taking Spanish? 37%. And I'm going to write the probability of Spanish or, what is it? French. Equals 37% for Spanish plus 15% for French, which means that the probability that a student chosen at random is taking a foreign language is 52%. You just add the percentages together. And hopefully, like if you think about it, that should make sense. If I got a group of kids taking Spanish and a different group of kids taking French, and I add those two groups together, I get a total number of kids out of the population of the school who are taking a foreign language. So 52% there makes sense, hopefully. This is the formula you need for OR situations. It can be one or the other. Okay, classic ACT type problem here. Suppose you reach into a dish and select a token at random. Those little shapes are called tokens, apparently. What is the probability that a token is round or green? Are they mutually exclusive events? Can I be round and green? Yes, in fact I have two of them, right? So it says round or green, which means I'm using my OR probability formula. So I'm going to write the probability of round or green equals. Find the probability of round. So I'm going to count up the number of rounds that I have. 1, 2, 3, 4, there's 5 of them. Out of how many? 9. So the probability of round is 5/9. plus the probability of green, which is what? 3/9. Then I got to subtract what?
There's only two.
There's 3 greens. I got to subtract the probability of both occurring at the same time. How many ways do both of those occur at the same time? Round and green. There are 2 of them. 1, 2 out of 9. So I got to subtract 2/9. Well, 5/9 plus 3/9 minus 2/9 gives me what? 6/9. So the answer is C. Can I just what? Count it up. Sure. I need something that's round or green. Either one of those is a win for me, right? If I win $1 million, if I pull something round or green out of this little plate with my eyes closed, I win $1 million. How many ways can that happen? Well, there's these things that are round. 1, 2, 3, 4. There's 5 things there that are round. Or I could pull out something that's green. That one right there also fits the bill for a total of 6 things on that plate that I could pull to win $1 million out of 9. I wind up with the same answer. Mathematically speaking, this is the formula. Because of the fact that it's a simple figure with very few numbers on it and very few tokens on it, you can just count them up and get the same answer. What if I'm looking for a token that's square or red? Let's do the math way. So I would write P, what? Or red, equals probability of a square would be what? 3/9, thank you. Probability of red. These 3 here are red, yeah. So it's 3/9. Then what? Minus, what am I subtracting here? Say in words, not just 1. I know it's 1. What am I looking for to subtract? The probability of what? Square and red, yeah. So it's the probability of A plus the probability of B minus the probability of A and B. So A is square, B is red. A and B would be square and red. And we do have one of those. So we're going to subtract off 1/9 there, which gives me a total of 5/9. Again, because it's a very small amount of tokens, and we can probably do this pretty quickly, square or red, I have 1 square, 2 squares, I have 3 squares, and then I have 2 other red things for a total of 5 out of 9. Same answer. What about green or square? So the probability of green or square. Okay. What is it? There's 3 green things. There's 3 squares. There is 1 green and square. So we get a total of 5/9. Again, green or square. 1, 2, 3, 4, 5 out of 9. That last one, can you come up with 2 events that are mutually exclusive such that the probability of A and B is equal to 0? Think about it. So if event A was yellow and event B was circle, we don't have any of those here, right? So yellow and circle does not exist up here, so the probability of that is 0. Do we have another? Red and triangle. We only have 1 triangle and it's yellow. It's not red. So that's another mutually exclusive. Any others? Yellow and square, same thing. Green and triangle, same thing. So there are actually lots of mutually exclusives up here. I will write down the first one that we had. What was that one? Yellow and circle, just as an example. And that's the whole section.